for today. We have Gurmeher Kathuria, who's joined us this summer from UCLA. Gurmeher has been working with Luke over the summer, and today he'll tell us about their project together through the rotational fog, detecting planets around young and active stars.
Thank you for the introduction, Gwen. Good afternoon, everyone. Thank you for sticking around till the end of the symposium. I know I stand between you and a lot of delicious cake outside, so we're gonna try and get through this together. So as Gwen mentioned, this summer I was working with Dr. Luke Bouma, who's right there, and we were trying to find ways to detect planets around young and active stars. And before I really delve into what exactly went through with this project, I want to take a minute to actually discuss the bigger picture. And it's a picture that begins with a fairly simple yet important question. Why do we search for planets? And in the simplest sense, each new discovery tells us something new about planets and planetary systems. They force us to rethink what we know about these systems. And discoveries like hot Jupiters, sub-Neptunes, super-Earths really help us better understand the diverse nature of planetary systems. And they gently remind us that we are not the template for planetary formation. And who would have thought we are not the center of the universe? So that's a big indication. And when we discover these new worlds, we also try to find signs of life, which was something that Gavin really stressed upon. The idea of searching for atmospheres helps us understand whether life can exist in other worlds, whether it be intelligent life or even microscopic life. Every life's important. And the last, but certainly not the least important, which kind of stresses on the same vein of the first point, is that searching for planets actually helps us understand planet formation and planet evolution. And as I begin to contextualize my work this summer more with this bigger picture, I want to take another minute to actually discuss this concept of planetary evolution. You see, planets evolve fairly early and quickly in their lifetime. So evolutionary processes like planetary contraction and the loss of atmospheres happen at very, very quick timescales and like astronomical timescales at about like tens to hundreds of millions of years after planet birth. And even processes like orbital evolution through disk migration, which is one of the reasons why you see Jovian-sized planets really, really close to their host star, occur at these timescales of about tens of millions of years after planet birth, when the protoplanetary disk is still active and can help with angular momentum interactions. So what I'm really trying to underscore here is the fact that it's important, if we want to study planetary evolution, it's important to look at planets when they're extremely young. And arguably, the most exciting chapter in a planet's life is its youth. But ironically, it's also the least explored. And if we look at the demographics of transiting exoplanets that have been found on the NASA Exoplanets Archive, we realize that about 1.5% of the planets that we've actually found are less than 1 billion years old. And this is a problem because we're not able to probe into planetary evolution based on this limiting factor of having a very small sample size. And this furthers the need for us to actually look for planets that are young. So we've established that there's a need to search for more young planets. But the next question that comes up is, well, where do we really look? And when we start scanning our local solar neighborhood for stars that are less than 50 million years old, which is the stars that young planets would be orbiting around, we notice this heavy little concentration of stars about 130 parsecs away that contain a lot of these pre-main sequence stars, or stars that are less than 50 million years old. And this region happens to be Scorpius Centaurus, or SCO-CEN. And the fact that they have so many stars that are less than 50 million years old make them like the perfect hunting ground for young planets. And so with the hunting ground established and the motivation established, the next question that comes up is, how do we really find planets around them? And you got a little bit of a spoiler alert from like Serena's presentation, so I'm going to be repeating a little bit of what Serena said. So just pretend that you were surprised. But what we do is we use this thing called the transit method, or transit photometry, which can best be explained by this little animation that I made. So in an ideal world, with the planet aligned perfectly with the star and with our line of sight, when a planet eclipses its host star, we see this drop in brightness that then our space telescopes can pick up. And as it leaves, we see on the ingress and the egress this dip and then return back to normal at 1.0 normalized flux. And in an ideal world, this would be amazing and it would make life much easier. But as you all might know by now, in astronomy, nothing is easy, nothing comes easy, and SCOSEN is no different. The stars that are in this complex are extremely, extremely active. So they flare incredibly often on timescales of days and hours. They have a lot of star spots, like the sun, but just higher in number. And to make things worse, they also rotate very rapidly. So instead of seeing these simple dips in brightness, you see this sort of sinusoidal variation. And in some cases, if the rotation period is extremely fast, like in this case, it can completely drown out the transit. And that's a big problem, because if we can't find the transit, we cannot find the planet. So what we've done over the summer is try to find a way to see through this rotational fog and actually detect planets around these active stars. So the methodology and the methodology that we adopted was fairly straightforward. We began with this literature compilation of SCOSEN stars that were imaged by the Transiting Exoplanet Survey Satellite, or TESS for short. And these were images taken from December 2024 until fairly recently in, I believe, June or July 2025. And once we got this data from TESS, we had to process this data first off. And the first step in this was to remove any flares using a windowed slider. After removing these flares, we decided we had to detect the rotational period of these stars and then detrend the light curve and the rotational variability using, again, a windowed slider. Now, I know I've mentioned the word windowed slider twice, so I'm obligated to explain what it means. And in the simplest sense, I can explain with a diagram. The way the windowed slider works to detrend light curves or flatten light curves is as follows. So you have a signal, a gray signal, and the gray line is the signal in this case, and you place this yellow window of fixed width centered at each successive data point. And essentially what happens is, as you slide through the light curve, you find the weighted average of each window centered at each point. And essentially, if a window is centered at one point, the total number of windows will be the total number of data points that you have. And what that would do is each red dot that you place will eventually trace out this trend line that can then help us detrend the light curve. Now, obviously, this is not doing a very good job. And there is one main reason why this process underfits for the data. That is, it doesn't really capture the amplitude. And that's because this light curve, we have a really large window length. So the idea is that if your window length, or the width of this yellow rectangle, is huge, it smooths out the rotational signal, because it's just looking through too wide a region. So it looks through these low dips while it's also scanning through the upper dips. So when you look at the weighted average that it calculates after calculating the median, it tends to underfit our light curve. So the next step would be, well, what if we completely shrink this window size and this window length? And we can do that for sure. That is an option. But what happens now is these transit dips are distorted by the fact that it's going to catch literally every small variation if our window length is too small. So the idea of detrending and this demystification of detrending is to find this Goldilocks zone, which is to find the perfect window length such that we're able to find and detrend the light curve, account for the rotational variability, while also preserving transit signals. And that had been a huge pain over the summer, but we were finally able to figure it out. And once we had the flattened light curve, we decided to use a detection algorithm, a transit detection algorithm that could help us find and detect the dips in our flattened light curve. After which, it was a simple process of visualizing and actually vetting through these light curves, which I will elaborate on as well. But just a complete look at our pipeline to actually see this in action on an actual star. This is the rotational variability. It's been to 30 minutes. In reality, the signal comes out every 2 minutes. That's the cadence of TESS. The blue markers are what we think are the transits occurring in this star. And once we've detrended the rotational variability, we get a flattened light curve. upon which we run this transit detection algorithm. On the right, what you see is a power spectrum. The peak that you see here is the orbital period that we found. So the way we measure the strength of our signal is through something called signal detection efficiency, which I can get into if required. But in the simplest sense, we see a good peak coming out of all this noise, and that's like a good indicator for us that there is something out there. We did set our threshold as 10, and I can talk a little bit more about why we did that if anyone has any questions on that. So as an exoplanet hunter doing transit photometry, these signals, these peaks are amazing to see. Unless this threshold of 10 is being crossed by eclipsing binaries, number one oppositions of us transiting exoplanet hunters. And to the untrained eye, this might seem like an amazing signal because the SDE, the power spectrum's peaking at 25. This is the cleanest signal I've ever seen. And to the untrained eye, it might seem like, hey, this is amazing. But what you see is, yes, there is a primary dip, but there is this secondary eclipse. And Serena did explain to us why this is a problem. But what this infers is that it tells us that there is a secondary star rather than a planet that's causing these dips. And that's a big problem, but our pipeline doesn't really account for this automatically. So we have to do this manually. And that's really painful because I like to compare it to like spam emails. You just have to clear out. You have to keep vetting them because there's nothing that automatically clears it out. Google has that. So, but yeah, so that's something that we just have to do manually, and it's really problematic. But yeah, after doing this manual vetting, what did we really find? So we had a sample of 5,000 stars, out of which 85% of them were rotators. 19% of them, of these rotators were actually extremely rapid rotators, that little simulation I showed. And those are really hard to find transits around, so we really didn't look at that. So just ignore that. And we recovered a number of known TOIs, test objects of interest blind. These are things that other people found interesting. So that was a good indicator for us. And it told us that, hey, we're on the right track. So that was a good indication. We also found that 9% of the stars actually exceeded our threshold cut, out of which 3% were planet candidates. And we have about a dozen planet candidates today, a few of which may survive further vetting. The other 6% are either eclipsing binaries, of course, or any edge case triggers or data gap triggers. And one of my favorite planets or IDs was this TIC 88297141. It's one of my favorite planet candidates because if this is confirmed, it'll be one of the youngest transiting planets that we've found at only about 15 million years of age. It'll have a radius of about 70% that of Jupiter, and it'll have an orbital period of 5 days. So if we do confirm this, we can look at planet atmospheres. We can search the atmospheres using James Webb Space Telescope, and we will steal your telescope time. So that's something we're really looking forward to. So just a little bit of a conclusion and next steps. We realize that studying young planets is extremely important to study evolutionary processes, and we've been looking for such planets in SCOSEN. We used a windowed slider to detrend these light curves, and we've actually been developing a more robust process the past few weeks, known as Notch, which I'll be happy to discuss at any given time. And we created this planet candidate list that we plan to follow up with recon radial velocities through the Magellan fire spectrograph, and eventually through seeing limited transit photometry. So with that out of the way, thank you for your time. Thank you.
Questions for Gurmeher?
Great talk. Thank you. My question is related to so Serena's result of a hot Jupiter that did have a secondary eclipse. I'm wondering with your search, how are you able to tell for certain that these are binary systems and not planets that have that secondary eclipse?
Okay, so I wasn't here for most of Serena's talk, but I can explain ways we do figure out how something is an eclipsing binary as opposed to an exoplanet. First off, it's just the dip in itself, how deep the primary eclipse goes. Usually if you're seeing these type of like transits happening with planets, they don't go down to like 15% of like a dip in brightness. So that's the first indication of it being a planet, not being a planet. The second reason is actually the shape of the dip as well. Usually when you look at planets, at least planets that we're looking around like M dwarfs, we're looking at smaller stars. In Serena's case, I believe she was looking at an F-type star, which is huge. But the shape of these transits, if they look V-shaped, they're more than likely caused due to eclipsing binaries. But a more U shape, such as this in this case, this little U, is something that you'd see from planets. And another way to check actually is through obviously radial velocities. That's why we don't completely shut them out. But you can also look at, this is not recommended, but we did this extra thing where we went to the Gaia DR3 database, and we checked something called RUI, which is renormalized unit weight error, which tells you, okay, if a star is supposed to follow a particular path in the sky, and you can fit a model to it, but it's not doing that, well, what's like it's like a chi-square difference type of test, but how varied is it from its path? And usually if you see that that's extremely high, that probably indicates that it's being pulled by something. It's a statistical value, so it's not to be trusted, but that's an additional step you can take. And also, Serena's case is an exception. Like almost literally every star and every planet, if it transits, will not have a secondary eclipse this pronounced as well. This could pass off as like a primary eclipse for context. So the fact that a secondary eclipse is this deep tends to point towards a stellar companion. Yeah.
Other questions?
I'm very interested in the window slider method. It's something we typically do from anyway in a different context. So I was wondering, how do you optimize for the window size? Yeah, do you have like some cost function that you are maximizing?
So is your question mainly like how do we decide on the window length that we want to use?
Yeah, you said you have some magic way of finding the perfect size of the window.
The magic way is not really magic, but the way we did it was we actually tested through a number of different windowed sliders. So we started off at 10%. So that's why actually finding the rotational period is incredibly important, because the idea is that if you just put an arbitrary value, and the rotational periods fluctuate a lot even within a complex. So if in this case the rotational period is in arbitrary units, let's say at around 5, and your window is 5 units long, it's literally going to just take this entire like the entire rotational trend, it's just going to flatten out at 0. So the idea is that you want to make it small enough and cater it to every star. So what we did is we found the rotational period, and then our slider was set at like 10% of the rotational period, or 15% of the rotation period, 20%. And we found like the best sort of results between that 10 to 20 range, 10% to 20% range, because after we hit 30% of the rotational period, it started underfitting. So that was our magic method. There is the other method that we're adopting, the notch flattening method, has a very strict cutoff, which states that if there's any star that has a rotation period less than 2, you use a window of half a day. And if it's anything greater than 2, you use the entire day as your window. And that's just because that method is just more robust at detecting rotation variability. This is a simpler method, I'd say statistically simpler method. It just looks at the weight distribution and weighted averages. So we have to be more careful with our window lengths in this case. Yeah.
Great. Thank you.
Of course.
All right. I think we will thank Gurmeher for his presentation.
Very nice job.